Welcome to Lecture 6 of Anthropology 330, Hunters and Gatherers. In this lecture, we'll be looking more closely at the role that food sharing plays in the foraging niche. As we saw in the first week, a key feature of the foraging niche is the sharing of food resources among family and band members. The ethnographic record shows that food sharing is pervasive among hunter-gatherers. From an evolutionary perspective, food sharing is a puzzle. An organism that gave away resources to another organism would increase the recipient's fitness and reduce its own. Thus, mutations that motivated such behavior would eventually die out. This raises the question, how could sharing evolve? Does sharing provide any fitness benefits? This is the general problem that Hill and Kaplan investigate in their article. What factors determine the occurrence and extent of food sharing among adult conspecifics? In their article, Hill and Kaplan review the four main hypotheses that have been advanced to account for the evolution of food sharing in animals, including humans. These are kin selection, tolerated theft, reciprocity, and cooperative acquisition. We'll look at each of these hypotheses in turn. As we saw last week, kin selection theory predicts that selection will favor the giving of assistance to kin, including food, when the cost to the giver is less than the benefit to the receiver divided by their degree of relatedness. Hill and Kaplan expressed this formula somewhat differently, but it means the same thing. This implies that the value of the shared food must be lower to the giver than it is to the receiver. It's not surprising, then, that the overwhelming majority of food sharing occurs between parents and offspring, because parents and offspring are closely related, sharing 50% of their genes, and because immature organisms are least able to provide food for themselves, and so benefit the most from food transfers. The second most common form of food sharing is also between closely related kin, but not as closely related as parents and offspring. This kind of sharing involves sharing between young and their older siblings or their parents' siblings, that is, their aunts and uncles, and, as we saw last week, is also referred to as allomothering. This kind of sharing is particularly prevalent among territorial nesting birds, which is why such helpers are referred to as helpers at the nest. It tends to occur when establishing a territory is a prerequisite for mating or successful reproduction, and an individual fails to establish a territory. It may also occur when the helper's own nest has been destroyed or the helper's brood has failed to survive. In either case, the best available option might be to feed the young of close kin. Thus, food sharing with kin occurs when the costs of sharing are low. In both of these sharing patterns, the transfer is from adults to young. It's obvious why food sharing occurs between adults and juveniles in humans. Children don't have the size, strength, or skills necessary to acquire most of the nutrient-dense resources that make up the human diet. But the disparity between adults in resource acquisition ability is less than that between adults and children. Although adults vary in their resource acquisition ability, with some men being better hunters than others and some women being better gatherers than others, most healthy adults have the size, strength, and skills to provide for themselves. Thus, we would expect the benefits of food sharing to the receiver to be lower for an adult relative than for a juvenile relative. This would be true if it weren't for the fact that some of the most nutritionally valuable resources that humans use come in very large packages and are very unpredictable. Humans hunt animals that are larger than they are, a very large package indeed, and that they can't entirely consume before the meat starts to rot. Thus, the benefit of keeping a large kill for oneself is lower than the benefit of sharing a kill with a relative. Moreover, for any given hunter on any given day, the odds of killing a large game animal are low, and a hunter can't predict when he will be successful. Thus, it's to a hunter's benefit to share with his relatives when he makes a large kill, because he makes them obligated to share with him when they make a large kill. On this view, food sharing reduces the likelihood that on any given day an individual will not have meat to eat. In sum, then, kin selection theory predicts that humans will give food to kin when the benefit to the relative outweighs the cost to the giver divided by their degree of relatedness, and that these conditions are most likely to be met with resources that are unpredictable and come in very large packages. We now turn to the tolerated theft hypothesis. As we just saw, food resources that come in big packages, such as large game, have diminishing returns. If the surplus meat can't be preserved or traded, it will begin to rot before the individual can consume all of it. Thus, this surplus meat is of little value to the person who possesses it. As Hill and Kaplan put it, at some point, additional units of the food resource are of less value than earlier units. However, odds are there will be someone in the group who is hungry and has little or no meat to eat, and the hunter's surplus meat is of great value to this hungry individual. All things being equal, a person to whom a resource is more valuable should be willing to fight longer and harder for it than a person to whom the resource is less valuable. Thus, when some individuals acquire large amounts while others acquire none or little, the tolerated theft hypothesis predicts that possessors will permit non-possessors to steal portions from them because the cost of defending the portion is greater than the value of retaining it. In other words, possessors allow non-possessors to take the surplus meat because to the possessor it's not worth fighting over. This brings us to the reciprocity hypothesis, which is also known as reciprocal altruism. We've seen why individuals share with kin, because when they do so, they're helping copies of their own genes. But this then begs the question of why individuals would share with unrelated individuals, a phenomenon that is very common in humans. Trivers came up with a hypothesis to explain this seemingly altruistic behavior. He argued that helping behaviors could evolve in the absence of genetic relatedness if the following conditions were met. First, individuals bear some cost which benefits other individuals. Secondly, the individuals who bear the cost receive some benefit from the individuals that they benefit. And finally, for both individuals, the benefits are higher than the costs. Acts of reciprocity can be divided into two kinds: tit-for-tat reciprocity and trade. Tit-for-tat reciprocity is when a unit of value is transferred from one individual to another in exchange for an equivalent unit at a later point in time. Grooming is a case in point. Jane grooms John now, and later John grooms Jane. For this form of reciprocity to evolve, two conditions must be met. First, for each individual, the value of the unit received is greater than the value of the unit given. And secondly, individuals who do not reciprocate achieve a lower net fitness than those who do. For example, if an individual acquires a large package of food, a fraction of that package should be less valuable to him than it is to an individual who has no food. The possessor will achieve a net fitness benefit if he can exchange that fraction of the food resource for an equivalent fraction at another point in time when he has little or no food. In order for tit-for-tat reciprocity to develop in a breeding population, the problem of cheating must be solved. Cheating is defined as accepting a benefit without reciprocating. An example would be if one of my group members shared meat with me when I was in need, but then I didn't share meat with them when they were in need. All things being equal, individuals who cheat will out-reproduce individuals who don't. This is because helpers incur fitness costs when they help, but don't get any benefits, whereas cheaters get benefits, but don't incur any fitness costs. Eventually, all the helpers will die out, and the breeding population will be filled with cheaters. Thus, the helping of non-kin cannot evolve unless the problem of cheating is solved. One way to solve this problem is to impose a cost on cheating, to make cheating more costly than reciprocating. And one way to impose a cost on cheating is to refuse to help anyone who is known to have cheated. The cost of cheating is that no one in your group will ever help you again. We would therefore expect humans to discriminate between those who have and have not given in the past, because individuals who gave in the past should be more likely to give in the future. By giving to those who have given in the past, the individual will be more likely to receive in the future. The second form of reciprocity is trade. In trade, resources of different currencies are exchanged. This exchange may be immediate or delayed. An example of immediate trade is the feeding of juveniles by subadult birds in exchange for access to high-quality territories. In this case, the provisioning and the territorial access occur simultaneously. Here there's no possibility of cheating, that is, of not reciprocating, because both resources are being given at the same time. An example of delayed trade is male-female meat sharing among chimpanzees. Males are more likely to share meat with estrus females and frequently mate with them after having given them the food. In other words, it appears that males are trading meat for future sex. The final explanation for food sharing that Hill and Kaplan discuss is cooperative acquisition. Some argue that social carnivores such as lions, wolves, hyenas, and African hunting dogs, and also perhaps baboons and chimpanzees, hunt cooperatively in order to increase their chances of obtaining prey, while some argue that food is shared among these groups so that individuals will cooperate in the hunt. These arguments are not mutually exclusive. If the spoils of cooperative hunting weren't shared, an individual could not be assured of a portion, and thus cooperative hunting would not necessarily increase the individual's chances of obtaining prey. There's some debate over whether individuals share the spoils of the hunt in order to get others to cooperate in the present hunt, or whether they share the spoils of the hunt in order to get individuals to cooperate in future hunts. But the answer is probably a little of both. If an individual cooperates in a hunt and doesn't receive a portion of the kill, he or she may leave the group, thereby reducing its cooperative hunting effectiveness. Or he or she might fight the others in order to receive a portion, possibly injuring some of them, which again reduces their hunting effectiveness. but it's equally plausible that an individual will be more likely to cooperate in future hunts if he or she has participated in a cooperative hunt and received a portion of the kill. As Hill and Kaplan note, neither of these hypotheses has been tested. To test these hypotheses, Hill and Kaplan generated a set of predictions for each hypothesis and then tested them using food sharing data. The population that they used for their study, that is, the population in which they collected their data, is a group of Ache foragers. The Ache live in subtropical eastern Paraguay and combine foraging with swidden agriculture in settled mission communities. At the time of the study, most Ache individuals were still foraging for up to 2 weeks a month away from the mission. Hill and Kaplan collected food consumption data on a total of 9 foraging trips for a total of 81 foraging days. Food consumption was monitored in 4 different ways. By recording entire day's activities related to food acquisition and consumption of a single adult randomly selected, by recording the activities of all persons in observation distance every 10 minutes throughout the day, by recording all the consumers of a particular food, and by dividing the campsite into regions and recording all the consumption activities of the individuals located in each region. For every consumption event, the following information was recorded: the consumer, the resource type, the original acquirer of the resource being consumed, and, where possible, the amount by visual estimate. We'll look at each set of predictions in turn, beginning with the kin selection hypothesis. Prediction 1 is that, other things being equal, food sharing will occur most frequently between very close kin. And prediction 2 is that the benefit to kin of shared food divided by the cost to the giver should be greater than the reciprocal of the genetic relatedness between the giver and the recipient. As shown in Table 2, prediction 1 was unsupported. With the exception of 2 gathered resources, Varela and Corilla fruits, the majority of the food was shared outside the nuclear family. Prediction 2 was not tested. For the tolerated theft hypothesis, Hill and Kaplan's predictions were that 1. Food will be shared only to the extent that the cost of defending it is greater than the benefit of keeping it. 2. Other things being equal, differences in resource holding potential will predict asymmetries in resource distribution. And 3. Large packages that are non-synchronously acquired will be shared more than small ones synchronously acquired. You may be wondering what non-synchronously acquired resources are. These are resources that are not acquired at the same time by everyone in the band who pursues them. Large game is a case in point. On any given day, several men will go out hunting, but odds are only 1 or maybe 2 of them will make a kill. Thus, large game is not acquired at the same time by all who go out in pursuit of it. In contrast, on any given day, a group of women will go out foraging, and all of the women will collect some of the gathered resource. Amounts will vary from woman to woman depending on how speedy, tired, distracted by childcare, and so on each woman is, but each woman will bring home some of the gathered resource. Thus, gathered foods, such as nuts, berries, and tubers, are synchronous resources. Predictions 1 and 3 are supported by Hill and Kaplan's findings. They found that acquisition variance and package size accounted for a lot of the differences in sharing between resource classes. Acquisition variance, which they also refer to as standard deviation across families, refers to variation between families in the amount each family acquires of a given resource. And package size refers to the amount of calories provided by a given resource package, for example, a basket of nuts, a hive of honey, a peccary. Hill and Kaplan divided the food resources used by the Ache into 3 categories: collected resources, honey, and meat. As shown in Table 3, there are clear differences in acquisition variance and package size for each of these food classes. First, there's more acquisition variance in honey and much more acquisition variance in meat than in collected resources. This is another way of saying that meat and honey are non-synchronous resources that are not acquired at the same time or in roughly the same quantities by everyone in the band who pursues them. Secondly, meat and honey come in larger packages than collected resources. In sum, on any given day, some families have meat or honey, while other families have little or none. And because meat and honey tend to come in large packages, the families who have meat or honey tend to have more than they can use. Since it's not worth expending calories and risking injury to defend a resource that you don't need, it makes sense to share the surplus with others. This is exactly what Hill and Kaplan found. Meat and honey are shared much more than collected resources are. However, Hill and Kaplan found that several features of the Ache sharing pattern are inconsistent with the tolerated theft hypothesis. First, hunters eat from their own kills significantly less than other individuals. If hunters were concerned about meat being stolen from them, they would eat as much of the kill as they could before others arrived. Instead, they save it for consumption by the entire band at the end of the day. Also inconsistent with this hypothesis is the fact that food is often saved for individuals, both men and women, even when they're not present when others are eating. Also, a man who finds honey will sometimes call for another man to chop the tree to extract it so that he can continue hunting. Although he'll receive a share of the honey later in the day, he'll miss out on the consumption when it's first extracted from the tree. Finally, although informants report that there's a great deal of variation among Aceh men in fighting ability, these differences were not reflected in the distribution of food. In other words, men were shared with regardless of their fighting ability. Prediction 2 of the tolerated theft hypothesis is that differences in resource holding potential will predict asymmetries in resource distribution. Resource holding potential is a technical way of saying fighting ability, and asymmetries in resource distribution is a technical way of saying sharing unequally. So, in other words, if a hunter shares less with some men than with others, we would expect this to be determined by the fighting ability of the recipients. We'd expect a hunter to share less with a poor fighter than with a good fighter. This is because the poor fighter is not likely to fight over the amount he is given, because he's unlikely to win the fight. In contrast, it might be prudent to be generous with a good fighter, because if he feels like he hasn't been given enough, he might fight about it, and he's likely to win the fight. However, Hill and Kaplan did not find any evidence that Aceh share unequally, so this prediction was not upheld by their study. For the tit-for-tat reciprocity hypothesis, Hill and Kaplan's predictions were as follows. First, the cost of giving a unit of food at time t will be lower than the benefits of receiving an equivalent unit of food at time t plus 1. Second, the net positive fitness gains from sharing with reciprocators will be greater than the costs of giving food to non-reciprocators. And 3, as with tolerated theft, large packages that are non-synchronously acquired will be shared more than small ones synchronously acquired. Predictions 1 and 3 are supported by Hill and Kaplan's findings. Their finding that meat and honey are more widely shared than collected resources is in keeping with prediction 1, that the cost of giving X amount of food when you have lots of food to spare is less than the benefit of receiving the same amount of food at some point in the future when you have no food. It's also in keeping with prediction 3 of the tit-for-tat hypothesis that large food packages that are non-synchronously acquired will be shared more than small ones synchronously acquired. This brings us to the cooperative acquisition hypothesis. Hill and Kaplan predicted that 1. Cooperatively acquired foods will be shared more than foods which are solitarily acquired, and 2. That individuals who cooperate in the acquisition of a resource will consume more of that resource. These predictions were not supported by their findings. There was no difference in sharing patterns between cooperatively hunted foods and solitarily hunted foods. The mean percentage of food shared outside the nuclear family of the acquirer was 92% for solitary acquired resources and 91% for cooperatively acquired resources. These findings imply that cooperative acquisition is not a necessary condition for food sharing. And this concludes Lecture 6. In the next lecture, we'll look at various tactics foragers use to maintain cooperation and prevent conflict.